And now I'd like to introduce the first speaker of today. This is Marco Fariselli. He's been an embedded engineer for 3.5 years at Greenwaves. And before that, he got his degree at the University of Bologna with mention. And he's been working previously also on ultra-low power machine learning and memory constrained systems. But today he's going to talk about a TinyDenoiser, an RNN-based speech enhancement on a multi-core MCU. So welcome, Marco.
Thank you. Thank you, Andreas. Thank you very much. Yeah, I'm Fariselli Marco. I work as embedded machine learning engineer at Greenwaves. And today I'm going to present the TinyDenoiser, which is our internally developed RNN-based speech enhancement model. And more importantly, the methodology that we developed to deploy such a kind of architecture into a multi-core processor like our latest chip, GAP9. This work was made in collaboration with Emanuele Rusci, which is not here today, but it's a research fellow at QLive and now worked with us for many projects. So before starting into the deployment part, let's understand what is the problem. Speech enhancement for us is the process of improving the voice quality in audio signals. So in other words, taking an audio signal, processing it in order to reduce everything which is not human speech, and improving the quality of the human speech out of audio signal. With the advent and with the popularity of AI, these sort of problems are starting to be solved with neural networks. And the quality of the solution based on neural network outperforms classic DSP solutions. And so the importance of bringing NN into speech enhancement systems. The classic approach, which you can find in literature for this kind of problems, is to take windowed time signal from the time domain, bringing it into the frequency domain, apply a deep learning model, and bringing it back to the time domain. This being done window by window by overlapping and adding each time frame windows. Note that it's extremely challenging to deploy such a solution into an embedded device, since the real-time constraint that is defined by the step between two consecutive windows is really restricted. And deploying such a solution into an embedded device is extremely challenging. If we then look further into the classic approach that machine learning engineers have developed to solve this problem, we can see that most of the work propose RNN-based solution, where you have a topology that more or less look like this, with an encoder-based architecture, a series of recursive neural network layers, and a decoder at the output to predict the frequency vector, which will be then back ported into the time domain. And the interesting part of RNN layers, and the reason why most people are solving this problem with RNN solution is manifold. But principally, it's because RNN layers predicts their current output based on the current input and the previous input. And they have an infinite, theoretically infinite history in the past. And this is very important for audio signals, where your current output really depends on what you heard so far. And the fact that you're doing it internally, using an internal state to store this infinite memory, doesn't require you to store a hugely wide input, which you would require in classic CNN approaches. They have, however, many problems, especially for what concern deployment. They are intrinsically memory bounded. They are basically just a matrix multiplication. So and they are very low operation over parameters ratio. This means that for each parameter that you move, you just do one operation, and you don't have any reusage of the weights that you load in memory. And this is really challenging from a computer architecture point of view, and it's really challenging problem to accelerate. And another point, which is kind of more general, not only for RNN, but when you are trying to develop audio pipelines, quantization, it's really challenging because the noise that the quantization introduces to the signal creates a lot of artifacts and makes it really challenging to quantize such solutions. And we all know how important quantization is for an embedded device. So during this presentation, I will try to show you how we solved all these issues. In this work, we present an optimized hardware-software design to bring any LSTM, GRU, so recursive neural network-based network into a multi-core system. We propose a mixed quantization approach that mixes floating point and integer inference into an embedded device. And we provide a latency and power analysis on a real implementation. Before starting looking at the choices that we made, we need to understand the architecture of the target. Otherwise, we don't get why we did things. So this is a really simplified diagram of GAP9, our latest multi-core processor. And you can find it here in the bottom. It has the peculiarity of the chip is that it has a compute unit, which is a cluster of many cores. They are RISC-V cores, with a cluster controller that controls all the synchronization between the cores and orchestrate all the operations between the cores. And then when you have a DSP or an N to accelerate, or any DSP operation, you can parallelize it over the 8 cores that can do the job. The 8 cores also have floating point units, so you can also accelerate floating point operation. And this is very interesting for audio pipelines, as we will see. From a memory point of view, it doesn't have a data cache to reduce as much as possible the power consumptions, but it has, however, a hierarchical memory level approach, where you have a first level of memory, small but very fast to access, a second level of memory of 1.5 megabytes on chip, and on-chip flash memory for non-volatile things, let's say. Plus, you can also have off-chip memory when you have all the peripherals to access them. As I said, to access from the compute unit perspective, which is what you're interested when you're trying to deploy an algorithm, accessing the L1 memory, it's very fast. Every core can access it in one cycle. But accessing other levels of memory is very costly. For this reason, we have hardware units that move data in background of your computation. And this is completely hidden by the computation. And these are the DMA. We have 2 units, one that brings data from the L2 to L1, and one that is the micro DMA, that brings data from L3 to L2. And everything is can be done behind the computation because it's dedicated hardware doing that, not the cores. Oops, doesn't work. Okay, so let's look in this architecture. How do we map a real use case RNN? So first of all, we have all the model coefficients stored in the non-volatile flash. Okay, they are constants, so they can be stored in the on-chip flash, and if they fit, they can be in the 2 megabytes of flash. Then, for each layer, we need to execute layer by layer our network. So we bring the weights that we need into the closest to the chip, closest to the compute unit memory, which is the L1, so from L3 to L2, L2 to L1, and then we fire the computation. Note that, as I said before, RNN computational kernels are basically vector matrix products, plus some activations in between, but the large majority of the computation is in the matrix vector multiplication. So that's the core thing of the RNN, and it's important to understand that in order to accelerate it. So in this paradigm, the time, so the latency of the whole thing will be the sum of the latency of each layer, and each layer in this approach, this naive approach, will be the sum of the time of bringing the data from L3 to L2, the time to bring data to L2 to L1, and the time to compute it. And in this paradigm, we firstly hit a big problem, especially for a large network, the one that performs well. The first problem that you might hit is that even a single layer may not fit the L1 memory, which is very tiny. Okay, so how do you solve it? Well, you can think of splitting the entire tensor of weights into sub-pieces and bring the sub-pieces and doing the computation on the sub-pieces that we call tiles, and iterate over all the tiles of your entire tensor. In this way, you split the problem in something that can fit your internal memory. And we have tools that automatically finds the optimal sizes of these tiles, which is a not naive problem, and does this memory movement across the memory hierarchy for each tiles. Okay, so now we still have this paradigm for the latency of the whole. How can we make it even better? So we said that we have specialized hardware to move data hidden by the computation. So why don't we apply a double buffering mechanism? Why not? And that's what we do. Okay, so instead of bringing the weights and then compute it and then bring in the next one, while we bring while we are computing our RNN layer onto one tile, we are moving the next one into memory. And everything is hidden by the data movement and the computation. And the final, from a code perspective, in the final code, you will see something like a for loop that iterates over each tile. And before starting the computation of the current tile, it starts the data move of the next tile. And everything is pipelined in this way. So the summation becomes actually the maximum of the 3 times, okay? And this is useful because already sum become just one element. But can we go even further? Yes, we can. There are a few other things that we can do to optimize it even better. And one thing is the tensor promotion. So till now, we said, okay, we store the data in L3, and we move them from L3 to L2 and L2 to L1. Because typically, the L2 is a static RAM. It's not something for non-volatile things. But if you think about it, why maybe the whole tensor could fit the L2 memory, even though it's a RAM, right? So before inference, what you can do is to move the whole. Yes, another thing that I need to mention is the fact that the bandwidth between the L3 and L2 is much lower than the bandwidth between L2 and L1. If you look here, the bandwidth between L3 and L2 is just 1 byte per cycle, while the bandwidth between L2 and L1 is more or less 8 bytes per cycle. And if we stick to the RNN problem, which is that for RNN layers, the number of parameters is equal to the number of operations that you need to do, you see that even having a perfect computational accelerator, even if you go super fast on the computation, you will be bounded by moving the data. The 1 byte per cycle means that you cannot do much more than 1 Mach per cycle in the final RNN efficiency. So having data in L3, it's really costly. One thing that you can do is that you bring, before inference, you bring the whole weights tensor into L2 and you store them. So that when you run your actual network, you just need to bring data from L2 to L1 and not going through the whole chain of memory hierarchy. And this is what we call tensor promotion. So we promoted some tensor that could fit the static RAM before inference. Now, okay, we understand the way of mapping from a code perspective. Now let's see what we can do from a quantization point of view, because we all know how important is quantization when we talk about embedded devices. But we also know that can be problematic from a quality point of view. Here you have the actual architecture of the final model that we deployed, which we call the denoiser. And it's very standard encoder-decoder network. So we have one linear layer as encoder, two recursive layers, and two linear layers as decoder, as the topology that I showed you in the first slide. We deployed to make the methodology general, we used different flavors of the same model using different type of RNN layer, so LSTM and GRU, with different number of units, so with different sizes. And here you can see the 4 type of layers. They span between 1.2 million parameters to 0.4 million parameters. And interestingly, see that the percentage of parameters that are stored for the RNN layers are the vast majority. For the LSTM256, is 84% of the parameters are for the RNN. And this is an interesting fact which we will leverage. So to deploy it and look at the quality performance, we used PESC and STOI, which are 2 common metrics to analyze the quality of the denoised audio signal. There are metrics to compare the audio signal versus the completely ground truth without noise and see how much close they are, basically. And we can see that our first solution was the floating point full precision FP32 with a PESC of 2.78, more or less, for the best model. And as a first solution for deployment, we just statically quantized everything to float 16, and which is not even a quantization. It's a data-free casting of all the things into float 16 using vectorized operation and all the backend that we have in GAP9 thanks to the floating point unit. And as you can see, it's completely lossless. So it's data-free, completely free. Push a button, and everything is work perfectly fine from a quality point of view. But in order to accelerate, this is not the best solution. The best solution would be to go into more aggressive quantization, like int8. And that's what we tried after this, if it goes. We tried a full int8 quantization. It's much more lightweight. It's 2x compression with respect to the floating point 16. And we understood now how much important it is to compress the memory footprint. But the loss in the quality was not negligible. At 0.3 PESC loss, it's not negligible. You can hear it very well. There are some artifacts in the reconstructed audio. So what we, again, looked at is the majority of the parameters were stored in RNN. So we thought, why don't we quantize just them into int8 and keep the rest in floating point? And that's what we did. We did a mixed approach where we quantized just the RNN layers into int8 and keeping the encoder and decoder in full precision. And actually what we saw was that the PESC and STOI degradation was much more limited, and we could achieve a pretty decent quality with a compression rate that ranges from 1.4 to 1.7x with respect to the float 16, which is not bad. And this didn't need any expensive quantization-aware training. Everything was done post-training, which is even better because you don't need to employ some deep learning frameworks that supports all these things, which are rare. Then we analyzed our solutions in a real implementation. And we have looked at the final solution in 2 aspects mainly. The code efficiency, so the amount of Mach per cycle we were capable of achieving thanks to this deployment design, and the power consumption. And these are the two metrics that we analyzed. And one factor which is very important and for understanding all this graph was the amount of tensors that we couldn't promote with the weights promotion. So we had to keep in 2L3 because they couldn't fit our internal memory. We benchmarked it onto our chip, a 22 nanometer chip, which is GAP9. So first of all, you can see that the biggest models, both LSTM and GRU, are totally memory bounded. You can see the amount of weights that's stored in L3 spans between 46 and 57%, and they bound completely the overall performance of the model, which couldn't reach more than 1 Mach per cycle, which is very low in this kind of, we have 8 cores, and 1 Mach per cycle is very bad for us. We can do much better. But due to the memory bandwidth, we couldn't achieve much more than that. Sorry. Even for LSTM, and GRU with smaller RNN units, we can see that in floating point 16, so in the floating point 16 version, the maximum code efficiency, even if they could promote everything into the L2 memory, so the amount of weights that were stored in the first memory was 0%, still the efficiency couldn't go up to more than 2.2 Mach per cycle. When we employed instead mixed precision, we can see that we gain both in the fact that we employ SIMD operation for int8 vectorization, and we reduce the amount of weights that are stored into L3. So we relax the memory bandwidth that we see. LSTM and even the 128 versions are improving because of the SIMD operation. Even though promotion is still 0%, they can still improve the Mach per cycle. You can see that also, which is interesting for me, is the fact that now that you are not anymore so memory bounded, you have increased the code efficiency, so you are doing much more things, and the power consumption rises a little bit. Then, thanks to voltage and frequency scaling, we were able to scale down the voltage and gain quadratically in power, and we reduced the power consumption by 2 to 2.5x. By making the final solution, which is the GRU 128, with a latency of 0.57 milliseconds, which is way below the 6.25 millisecond real-time constraint, which was the op size between 2 consecutive windows. And if we consider even the biggest model, which is the LSTM256, and we consider the average power over the activity and the duty cycling over the non-activity of this 6.25 millisecond window, we can achieve an average overall power of less than 3 milliwatts for the RNN execution. So this I concluded. Our optimized design for speech enhancement has consisted in multiple elements. We have a multi-core acceleration, which vectorizes operation in float 16 and int8, but we needed a software pipeline to create an efficient code in order to interleave memory transfer. Then we applied tensor promotion in order to reduce the amount of weights and constants that we need to store far from the computational unit. And we employed a mixed quantization approach that mixes floating point and int8 operations in order to compress even further the memory footprint. Thank you. I want to mention that this work has been published, so if you're interested in digging into it more, you can find it on arXiv. We can pass by our booth. We have a demo that shows how it works, and you can try it out. Thank you very much.
Great, thank you, Marco. Questions, please.